Hello everybody. On this occasion, our group will be presenting you about simple linear regression and correlation. The group members are first, Ridhamelia, second, Frieska Ardi Anandiva, third, Annatasya Putri Salsabila, fourth, Alifeony Mutiara Diarsya. The content of the topic is first, what is simple linear regression? Second, the method of the least square. Third, properties of the least square. 4. Estimator of variance. 5. Assessing the utility of the model. 6. The coefficient of correlation and determination. 7. Using the model for estimation and prediction. Part 1 and Part 2 will be presenting by Ridhamelia. Part 1. What is the simple linear regression? Simple regression is the analysis of the single regressor variable in which the relationship between y and x is linear. Y given x equal beta 0 and beta 1 times x. This is the expected value of y for each value of x. Next, the intercept beta 0 and the slope beta 1 are unknown regression coefficient. We assume that its observation y can be described by the model y equals beta 0 and plus beta 1 times x plus epsilon. Epsilon is random error with mean 0 and unknown variance. Part 2. The method of the least square. The method of the least square is find b0 and b1, the estimate of beta 0 and beta 1. Next, you can sum of the square of the residual is a minimum. Next, the sum of the square of the errors about the regression line and is denoted by SSE. Last, minimization procedure for estimating the parameter is called the method of least square. You can find A and B so as to minimize. You can use the formula of SSE from this slide. Next, differentiating SSE with respect to B0 and B1. Then you can calculating by this formula. You can see. Next, setting the partial derivative equal to 0 and rearranging the terms. You can use the last formula on this slide. Next, the least square estimates B0 and B1 of the regression coefficient beta 0 and beta 1 are computed from the formula. First, the formula of B0, B1. You can see on this slide. Next, the formula of B0. You can also see on this slide.
Okay guys, so we are going to part 3. In the part 3, we are going to discuss about the properties of least square estimators. Before we're going forward, So part 3, I'm going to remind you about assumption that we used before at the method of the least square. That are first predeterminateness of the expected value of epsilon t given to xt sum as 0, and the second assumption is yt and xt are are stationary I'm sorry, and then the third assumption is there is no perfect multicality in xt. And then after that we can moving forward for the part 3. In the part 3 we are going to discuss uh, about the proportion, that is the estimators of b had 0 and b had 1 are unbiased. For this proportion, we need to make one more assumption, which is the assumption of the strict isoscity. The expected value of epsilon t given to x1 until xt are sum with 0. I'm going to annotate here, maybe. And epsilon t given to x1 until xt are sum with 0. And then for the proportion, that is the expected value of beta had 0 sum as beta 0, and the expected value of beta had 1 are sum with the beta 1. We have to prove it, which is we need to search or to find the beta hat 1. The beta hat 1 we can calculate it from the equation that we get from the part 2, and then the final answer for the beta hat 1 is this. Thus we have the conclusion that the expected value of beta hat 1 is this. And the conclusion of the expected value from beta hat 0 are this. And then moving on to the second proportion. Second proportion, we are going to discuss about the variances of beta hat 0 and beta hat 1. When the proportion said that variances of beta hat 0 are this, given to this, and the variances of beta hat 1 given to this. And then we need to prove it. Why we can get that? By calculated. And then from the variances of beta hat 1 we can get that that variances of beta hat 1 are this. Sum as the proportion that we estimate is not, but it's not estimate, but we discuss on the proportion, and we can calculate it, and then is it that proof that the variance of beta 1 sum. And for the variances beta 0, we have to calculate it, and then we can get the final answer by this equation. But at the variances of beta 0, we need to find the covariance of y and beta hat 1. Then the covariance of beta hat 1, we can get that is the beta that is covariance y and beta hat 1 is 0, and then the final answer, the variances of beta hat 0 for this. Okay, that's all for the part 3. Thank you.
So the part 4 and 5 for this presentation will be presented by me, Annatasya Putri Salsabila. Part 4 is estimators of variance. In most practical situations, the variance of the random error will be unknown and must be estimated from the sample data. Since variance measures the variation of the y values about the line EY equals to B0 plus B1x, it seems intuitively reasonable to estimate variance by dividing SSE by an appropriate number. There is actually another unknown parameter in our regression model. The residuals EI equals to YI minus Y hat I are used to obtain an estimate of variance. The sum of squares of the residuals, or we can call it SSE, often called the error sum of squares. This is the formula of SSE. So, we can show that the expected value of the error sum of square is E or SSE equals to n minus 2 times by variance. Therefore, an unbiased estimator of variance is SSE divided by n minus 2. For example, calculate the estimation for variance from the relation of compression and pressure data as the example. Y equals to minus 0.2 plus minus 0.6x, where n equals 4. So, the F for error is 4 minus 2 equals to 2. Part 5 is assessing the utility of the model. First one is making inferences about the slope B1. Refer again to the data and suppose that the compression of the insulation material is completely unrelated to the pressure. What could be said about the values of B0 and B1 in the hypothesized probabilistic model is Y equals to B0 plus B1x if x contributes no information for the prediction of Y. So the implication is EY equals to B0 plus B1x doesn't change as x change, or regardless of the value of x, always predict the same value of y. In the straight line model, this means that the true slope B1 is equal to 0. Therefore, for null hypothesis, for H null equals to 0, it means that x contributes no information for the prediction of y. And for H1 or alternative hypothesis unequal to 0, it means that x does contribute information for the prediction of y. So if the data support the alternative hypothesis or H1, we will conclude that x does contribute information for the prediction of y using the straight line model.
And the next is the coefficient of correlation and determination. Coefficient of correlation show how strong the relationship between two variables. The value of R or coefficient of correlation 0 less than R less than 1 we can find population correlation coefficient by using this formula, and we can also find sample correlation coefficient by using this formula. This is the chart of positive correlation. If the value of R is positive and then no correlation, if the value of R equals 0 and the negative correlation. The next is coefficient of determination, or R square, is the square of correlation coefficient. Next, using the model for estimation and prediction. Confidence interval on parameters. The parameters is the slope and intercept, or beta 1 and beta 0. We can find confidence interval on the slope by using this formula, and also we can find confidence interval on the intercept by using this formula. And if the equation is like this, may be used to predict or estimate the mean response at x equals x0. So we can find confidence interval for the mean response by using this formula. And then the degrees of freedom is n minus 2. And the last is prediction of new observation. We can predict the linear regression by using this formula, and also the value of degrees of freedom is n minus 2. And that's all our presentation. Thank you for your attention and sorry for all our mistakes. Assalamualaikum warahmatullahi wabarakatuh.